This is the Chemical Kinetics podcast, in which several sources of tabulations of thermodynamic information will be discussed. For each non-hydrogen atom, there is an associated set of thermodynamic values. Primarily, they depend on an atom in question and what atoms they are connected to. One sums up the values of each non-hydrogen atom. Further corrections are based on the steric effects. In the table, the heat of formation and the standard enthalpy are given along with the standard heat of capacity of the values at different temperatures. Together, we can calculate the necessary thermodynamic quantities at any temperature, or at least within a range. Benson rules assume that the effect of structure on the thermodynamics is additive. Each structure contributes a certain amount to the property. The structure in the Benson rules is an atom bonded in a certain way. Associated with each of these atoms is a set of thermodynamic properties to be added up. Atom descriptions consist of a center atom, such as carbon or oxygen, but not the hydrogen, and a list of atoms it is bonded to. Associated with each atom description is a standard enthalpy, a standard entropy, and a list of heat capacity values at a list of temperatures. The set of atom properties is found within the molecule or added up to give the final estimate of the thermodynamic properties. This is two typical Benson rules for common carbon types, a primary and a secondary carbon. The first atom listed is the center atom. The atoms in parentheses are the atoms this center atom is bonded to. With each rule, there are standard enthalpy and entropy values, along with a list of heat capacities. Heptane is a linear molecule having 7 atoms. The two end carbons, the primary carbons, are connected to 3 hydrogens and a carbon. This is denoted as CCHHH in the tables. The first symbol is the atom in question, and the atoms in the parentheses are the connected atoms. For heptane, the values in the Benson table are multiplied by 2, i.e., for each of the 2 primary carbon atoms. Each of the 5 carbons in the middle heptane are connected to 2 carbons and 2 hydrogens each. This is denoted by CCHH. For heptane, the values in the table are multiplied by 5, i.e. for the 5 secondary carbon atoms. The final added total gives the heat of formation, the standard enthalpy, and the heat capacities at 300, 500, 1000, and 1500 degrees Kelvin for heptane. Another source of thermodynamic information commonly used in kinetic programs is the NASA polynomial, meaning a polynomial fit to the thermodynamic information. This is, for example, used in ChemChem and is the de facto standard for combustion. 2 temperature regions are considered in the NASA polynomials: the region below 1000 degrees Kelvin and the region above 1000 degrees Kelvin. Actually, other dividing temperatures can be used, but 1000 degrees Kelvin is most common. The polynomial is an approximation in each region having 7 coefficients. From the 7 coefficients, the dimensionless quantities related to the temperature-dependent heat capacity, enthalpy, and entropy are derived. This is the NASA format in ASCII form. One valuable source of thermodynamic information is the National Institute of Standards from the US, the acronym NIST. If you look at the website, they have a webbook of thermodynamic and kinetic information. In fact, their values are actually considered to be very standard within combustion. Another older source in book form is the Janov tables. This is actually a book, remember those? And found in a library. Remember what that is? In any case, these are often used as references in many combustion mechanisms.